Uh, in the yesterday's lecture, we have seen design of IC engine components. Right? We have seen the parts to be designed in the IC engine. There are main components: cylinder and cylinder liners, piston rings, gudgeon pin, connecting rod, crankshaft and crank pin. Okay, again we have seen the cylinder liners having two types: wet liners and dry liners. We have seen the difference between wet liners and dry liners. Wet liners, the cylinder blocks are simple and hence easy to manufacturing, but in the dry liner, cylinder blocks are complicated and hence difficult to the manufacturing. Okay, this is the main difference. Then again, in the wet liner, cooling is more effective due to the direct contact of the water jacket, and in the dry liner, cooling is not very effective because of separate water jacket and the liners. Okay, and in wet liner, again see the replacement of the liner is difficult, but in the dry liners, the replacement of the dry liner is very simple. Then after that, we have seen the difference between the small engine and large engine, also cylinder liners, then types of the liners. We have seen the terminology. We have find out the mechanical efficiency with the help of brake power and indicated power. Also we have find out the bore diameter, then thickness of the cylindrical wall. T is equal to P max into D divided by 2 sigma C plus C. C is the reboring allowance. We have seen in the yesterday's lecture. Okay, then cylinder flange thickness, it is denoted by the TF. Okay, we have to see, and stresses in thin cylinder, already we have completed that part. Then stud, it is also called as a bolt. We have calculated the DC for that bolt or stud. Okay, also we have calculated the nominal diameter, core diameter, it is also called as a mean diameter. Then PCD of the stud, pitch of the stud, then number of studs. All we have seen all this formulae in the yesterday's lecture. With the help of that formulae, we will get one questions for the 10 or 12 marks numerical in the examination. Then how to solve that numerical? We'll see that first numerical. The okay, we'll see the numerical. The cylinder of 4-stroke diesel engine has the following specification. The specification are given: brake power CP is equal to 7.5 kilowatt. Then speed is given 1400 rpm. Then indicated mean effective pressure is given 0.35 MPa. The cylinder liners and head, you have given the material GCI FG 260. 260 means you have given the SUT 260 MPa. Okay, and stud having the plain CS 40 C8. The SIT value is given 380 MPa for the stud, and factor of safety for the all parts you have given 6 mm. Then calculate the bore and length of the cylinder liner. Then second, thickness of the cylinder liner. Third, thickness of the cylinder head. Then size and number of pitch of stud. Okay, this value we want to the calculate. See, this type of question will ask for the 10 to 12 marks. And how to calculate that bore and length of the liner? Yesterday we have seen the formula for the bore and length of the cylinder liner. Okay, how to calculate? You know the relation, L is the length of the cylinder, capital L. Okay, then there is a length of the stroke is given for small l. Okay, you know the relation between the bore diameter and length of the stroke. small l is equal to 1.5 d, capital D, or l is equal to, we can say, 1.5 d divided by 1000 because of meter. Okay, then we know the number of working stroke per minute, small n is equal to n by 2 because of 4 stroke is equal to 700. Then how to calculate the efficiency? Efficiency is equal to brake power divided by indicated power. Indicated power is equal to bp divided by n. We know that value in that equation. We know the equation ip, this value is given 9375 watt, this value is given, is equal to pm LAN divided by 60. In that equation, if you are putting the value, then you will get pm into 1.5d divided by 1000. And what is the area? Pi d square divided by 4. And what is the n value? N is equal to 700 divided by 60. Okay, then you will get the bore diameter d is equal to 124.9, equal to, I will write 125 mm. And length of the stroke, you know the relation, L is equal to 1.5 into D, means 125 into 1.5, you will get the 187.7 mm. And how to calculate the length of the cylinder? Again, you know the relation, length of the cylinder is equal to 1.15 into small l, you will get the 216 mm. Okay, all of you getting? If you know the formulae, then easily you can calculate with the help of given data. Second, we want to calculate the thickness of the cylinder wall. We are consider it is a thin cylinder. We know the formula, T is equal to P max into capital D divided by 2 sigma C plus C. Okay, then how to calculate the sigma T or C? Is equal to SUT divided by factor of safety. SUT divided by factor of safety. Okay, how to calculate this? To calculate the sigma T is equal to SUT divided by factor of safety, right? Yesterday we have seen this equation, SUT divided by factor of safety is equal to, you will get the 43.33 MPa. Then what is the C? C is the reboring factor. How to calculate that reboring factor? Yesterday we have seen one table is given, D is equal to and C is equal to. D is the cylinder bore diameter is given, right? Cylinder bore diameter is given 75 to 500 range. Related the boring factor, reboring factor is given related to that cylindrical bore. Okay, this value is given in mm. Then check that the boring factor. How to calculate that boring factor? We know that C is equal to 2.4 plus in bracket 4 minus 2.4 divided by 150 minus 100. 150 minus 100 is the diameter into 125 minus 100 is equal to 3.2 mm. 3.2 mm. Put all this value in the equation, T is equal to, then you will get the value T is equal to 8.5 or 10 mm. 10 mm. Okay, remember that this value will get the thickness of the cylinder wall is a 10 mm. Then stresses induced in the cylinder, we have seen the which type of the stresses induced. Then apparent stress sigma C. Sigma C is the circumferential stress is equal to P max into D divided by 2T. Okay, we know the P max value, we know the D value and 2T value. Okay, then put this value in that equation, you will get the answer 21.88 MPa. And how to calculate the outside diameter, DO? DO is equal to D plus 2T. Before that also we have seen in the pressure vessel. You will get the 145 mm. How to calculate the longitudinal stress? Longitudinal stress is equal to P max into D square divided by outer diameter square minus bore diameter square. If you are putting the value in that equation, then you will get the 10.13 MPa. Then net stress, how to calculate the net stress? Again, net stress is equal to sigma c minus mu into sigma L. Mu is Poisson's ratio, right? We have seen. Put that value in that equation, then you will get the C net. First value will get the 19.35 MPa, and second value you should replace the position of the sigma L. Okay, sigma L. Here we have calculated the sigma C. For the sigma L net is equal to sigma L minus, we are consider the positive direction, this, and which is the negative direction, circumferential stress is negative direction, that's why minus mu into sigma C, you will get the 4.66 MPa. The number of stud, it is denoted by the Z or N. Some books you have given the N, or some books you have given the N or Z. Z is the number of stud. Z is equal to, you know the formula, D divided by 100 plus 4, or 2 D divided by 50 plus 4. This value we will get the 5.25 to 6.5. Okay, then we will convert into the whole number or integer number. Z is equal to 6. We can't say the number of stud is equal to 5.25, right? This is the whole number or integer number, that's why we will take the next digit. Z is equal to 6. Then how to calculate the nominal diameter of the stud? Nominal diameter, it is denoted by the DC. DC is equal to D, capital D into root of P max divided by Z into sigma T. DC is the mean diameter or core diameter, right? Then how to calculate that DC? You will get the 12 mm. 12 mm. If you are putting the P max, Z and sigma T value, then you will get the DC is equal to 12 mm. The nominal diameter is denoted by the D. How to calculate? DC divided by 0.8. DC is 12. 12 divided by 0.8. You will get the 15 mm. Then how to calculate the tangential stress? Sigma T. Sigma T is equal to 3T divided by 6. Number of stud, 63.33. Then pitch of the stud. Pitch of the stud. How to calculate the pitch of the stud? You should calculate the pitch of the stud. DP is equal to PCD of stud, or you can use the D plus 3D. You will get the 170. Pitch of the stud pi dp divided by Z. Okay, use that equation. And range of the pitch of the stud is equal to 19 divided by root D to 28.5 into root D. You will get the range of the pitch of the stud is 73.59 mm to 110.38 mm. This is the pitch of the stud. This satisfactory range. We have the answer. Pitch of the stud is equal to 89.01. This is in between 73.59 mm to 110.38 mm. Okay, that's why the pitch of the stud is satisfactory. Then next is a piston. Okay, this is the main part of the cylinder. What is the function of the piston? Piston is a disc which is a reciprocate within the cylinder. It is either moved by or moves the working fluid which enters the cylinder. The function of the piston in IC engine is to receive the impulse from the expanding gas and transmit the energy through the connecting rod to the crankshaft. Okay, from the expanding gas and transmit the energy through the connecting rod to the crankshaft. See the main part of the piston. Piston ring is there, gudgeon pin is there, then small end connecting rod, and there is a big end bearing is given. Okay, the piston is used in the IC engine are usually for the trunk type, okay, which are a open at one end. There are different parameters we will discuss the reference to the design of the piston. Then which parameter will require construction of the piston? First parameter is a construction of the piston. Second is a piston head. Second is a piston head. It is also called as a crown. It is also called as a crown. Remember that. And third is a piston clearance. Piston clearance. Okay. Then we'll see one by one. First is a construction of the piston. Okay. There again we want to the see details. The before going on the construction of the piston, part of the piston. Okay. Then you have seen in the figure the piston is given trunk piston. There are consist of the different parts. First part is a piston head, or it is called as a crown. See, piston head or crown. The cylinder, the piston head or crown is withstand the cylinder gas pressure. It has a flat or concave shape. Okay, the shape of the piston head is a concave shape, and this is depend upon the construction of the combustion chamber. Okay, then second part is a piston barrel. Piston barrel, it is a support to the piston head and provide the seat for the piston ring. Okay, this part is provided support the piston head and provide seat for the piston ring. There are the two piston ring we are shown in the figure. Check that. What is the piston ring? Piston ring means seal of the cylinder, and it is prevent the leakage of the gases. Okay, if there is any leakage, then they are prevent the leakage with the help of piston ring. Then piston skirt is there. Okay, piston skirts is act as a bearing for the connecting rod side thrust. Okay, it is a acts as a bearing for connecting the rod side thrust. Then reinforcing rib. Ribs act as a stiffener for a piston head and piston skirt. Between the piston head and piston skirt, we are using the stiffener. It is also called as a reinforcing rib. Reinforcing rib. Okay, then next is a piston pin, or it is also called as a gudgeon pin. Okay, piston pin, or it is also called as a gudgeon pin. We'll see the details one by one. Right? Piston pin or gudgeon pin. It uh, consists of piston of the connecting rod. Okay, piston pin or gudgeon pin. This is the main part of the piston. Then we want to see the what type of material is used for make the piston. Okay, or what is the property of the piston material. Okay, piston material should have high strength so as to withstand the high gas pressure and inertia force. Inertia force. Okay, see this is the figure of the piston. Okay, there I have seen shown each and every part. Piston pin is there, skirt is there, ring section is there, top land is there, piston is there, groove compression ring is there, rib is there. It should be heat resistant so as withstand the high temperature. The temperature is so high, that's why this should be the bear resistance that temperature. Okay, it should be lightweight. Okay, not so heavy. Okay, minimize the inertia force if the lightweight. It should have the good thermal conductivity so the heat can be quickly dissipated. Okay, if you have the good thermal conductivity, the heat should be the quickly dissipated from the piston crown or piston head to the ring and the cylinder wall. Okay, then again it should have low coefficient of thermal expansion. okay, to minimize the expansion at high temperature. Again, it should be have uniform thermal expansion so as to avoid the distortion of a high temperature. This is the some property of the piston material. Okay, then we have seen the parts of the piston. Yes, piston material. Then again, any properties remaining, it should have the good bearing property also, good bearing property. Then which type of the material is used for the piston? Okay, we will see the details. There are cast iron, we are using the material cast iron. Okay, cast iron, what is the advantage of the cast iron? Cast iron has a good strength and good wear resistance, okay, at high temperature, because temperature of the piston is very high. That's why we require the good strength and good wear resistance. Also we require the low coefficient of thermal expansion. The cast iron having the low thermal coefficient of thermal expansion, but cast iron also having the some disadvantage as high weight and low thermal conductivity, okay, or we can say the high density of the cast iron. Use of the cast iron piston for moderate power engine with piston speed below 6 meter per second, the cast iron we can use. Then second material is a aluminum alloy. Okay, aluminum alloy, some in the piston we are using the aluminum alloy. Aluminum alloy having the lightweight, or we can say the low density, okay, and having the good thermal conductivity. The aluminum alloy is 3 times lighter than the cast iron. Okay, cast iron is a very heavy material. As compared to the cast iron, this aluminum alloy is 3 times lighter than the cast iron. The casting of aluminum oxide or tin or aluminum alloy piston, the it to the wear property. Okay, there is one disadvantage of the aluminum alloy with the reduction of the strength as high temperature. If there is a high temperature, then again the strength is a less of that aluminum alloy and high coefficient of the thermal expansion. This is the second disadvantage of the aluminum alloy. Then what is the use of the aluminum alloy in the piston? Okay, the strength of use in the aluminum alloy is 40% higher than the aluminum piston made by the casting. Okay, then we want to use the forged aluminum piston are used for the heavy duty piston. Okay, high speed cast iron engines, and for the aircraft we want to use the aluminum alloy for the high power engine also. Okay, with piston speed above 6 meter per second, then we want to use the aluminum alloy material. Third material is the alloy cast steel and alloy forged steel. Alloy cast steel piston are used for the sometimes in the automobile engines, while forged steel piston are used in the sometime some aircraft engine. Okay, then we'll going on the next design requirement of the piston. Okay, what is the design requirement of the piston? Should have we have discussed the different materials and strength of that material. Should have the sufficient strength, should have the sufficient rigidity, adequate capacity of the dissipate heat, means thermal conductivity of that material, should have lightweight, or we can say the minimum weight. Aluminum alloy having the minimum weight as compared to the cast iron, 3 times is lighter than the cast iron. Form an efficient seal to prevent the leakages. Okay, we have seen we are using the rings to prevent the leakages and noiseless operation. There is operation should be noiseless. Okay, then see the design of the piston head or crown. It is also called as a crown. The thickness of the piston head or crown can be determined by using the strength and heat dissipation. Okay, these two parameters are very useful in when you design the piston head or crown. The thickness of the crown is calculated based on the first is a strength as well as a heat dissipation. Okay, you have to check the strength as well as the heat dissipation, and larger of the two value we will select for the design of the thickness of the piston head. Okay, here you will get the two values, you will get the strength, also you will get the heat dissipation. Out of that two, which value is maximum, that value we are choose for the design of the piston head or crown. Okay, how to calculate the thickness of the based on the strength. Okay, the thickness of the piston head can be calculated considering the piston head, the flat plate. Okay, there are two types, flat head or cup type. Flat plate of uniform thickness fixed at the edges, see in the figure. Okay, and subjected to the uniformly distributed load due to the gas pressure. Due to the gas pressure, the thickness of the piston head is 0. Check that the formula 0.433 d root of p max divided by sigma all. Allowable, what is the thickness of the piston head? Ph. Tph is the thickness of the piston head or crown. Okay, this is given in mm. D is the diameter of the piston. P max is the maximum gas pressure, and sigma all is the allowable tensile stress. Okay, then see heat dissipation. Already I have told the heat dissipation, how to calculate with the help of heat dissipation. Okay, this is we are using the strength. Then heat dissipation, the piston almost some portion of heat from the gases which has to be transferred to the cylinder through the piston ring. Okay, and through the direct contact. If the heat is hot transferred to the cylinder, the piston get overloaded. Okay, then there are some conditions to avoid the overheating of the piston. Then how to uh, avoid the overheating? There is a formula of the rate of the heat absorption by the piston from the gases equal to the rate of the heat dissipation through the piston head from the to the cylinder wall. Okay, how to calculate that? Rate of the heat is will denoted by the q. Okay, q is the rate of q into pi t square is equal to k into pi r to tp into dt minus divided by dt. Okay, or you can use that formula th is equal to h divided by, there is one derivation is given directly. I have told that piston head absorb the heat during the combustion and transmit to the cylinder wall. th is equal to h divided by 12.56 k into bracket tc minus te into 10 raised to 3. Okay, and what is the capital H? Capital H is given for the heat conducted to the piston head. Heat conducted to the piston head. H is equal to, how to calculate that H value? H is equal to, in bracket, C into SCV into M into BP into 10 raised to 3. SCV is given in kg per joule per kg. Okay, this value is given diesel having 44,000 kg per kg, and for petrol 47,000 kilojoule per kg. Okay, what is the C? C is given for the heat absorbed by the piston divided by heat developed in the cylinder. This value is near about 0.05. You have given one table. From that table you should choose that value, okay, for the different material. M is the mass of the fuel used per bp per second, okay, and average consumption is given 0.24 to 0.30. K is given for the thermal conductivity, okay. Tc is the temperature of the center of piston head, and T is the temperature at the edge of the piston head. This K value and Tc minus T value you have to choose as per the material. If there is a, you have given the cast iron, alloy cast steel, aluminum alloy steel, okay, then allowable tensile stresses also given related to that material. If you have given the grey cast iron, aluminum alloy or steel, okay, related that you have given the thermal conductivity, okay, and delta T temperature is given. Delta T means again what is Tc minus Te. Tc minus Te. Again what is the Tc and Te? Temperature at the piston head in degree Celsius. Temperature of the outer surface. This is given Te. Okay, this two value is given. Piston ribs and cup. Next is a, okay, piston ribs and cup. Cup is the additional space at the top of the cylinder head. Okay, top of the cylinder head. This depend on the required volume of the cc and arrangement of the walls. Okay, what is the arrangement of your wall, and what is the additional space of the top cylinder? This is depend on this value. Then see total rib I have shown. See that rib or cup portion of the piston. If this value is given 4 to 6, then rib thickness Tr is equal to Th by 3 to Th by 2. Okay, use this formula and calculate the rib thickness. Calculate the rib thickness. Okay. Then second, see when L by D ratio, see again Th, there are some condition. Th is greater than 6 mm, then Th is less than or equal to 6 mm, and you should use the R and NR. Okay, when L by D ratio is greater than 1.5, then you should take the NR, and L by D ratio is less than or equal to 1.5 R. Okay, rib value, radius of this cup is 0.7 D. Okay, both value you should remember that. Okay, no need of the derivation, you should remember the only the value of the design of the reciprocating ribs. Okay, these two ribs you should take the value. Again see, I will explain. Number of ribs are used 4 to 6, then thickness of each rib is Th by 3 or Th by 2. You should remember that. If the thickness of the piston head is Th is greater than 6, then the ribs are required. Okay, ribs are R means what? Ribs are required. If the thickness of the piston head is less than or equal to 6 mm, then ribs are not required. Similar way, this is the L by D ratio. L by D ratio. L by D ratio is greater than 1.5, then ribs are not required, and L by D ratio is less than or equal to 1.5, then ribs are required. Remember that relation. Okay, then there is a piston ring. Design of piston rings. Okay, design of piston ring. What is the use of that piston ring? Absorb the functional inside thrust, then leak proof, transfer heat from the piston head to the cylinder wall. We have seen the rectangular cross section of that piston ring is most widely used in a compression ring. Okay, this compression ring is used. Second compression ring and first compression ring. See the figure of the piston. Okay, then to calculate the number of piston rings. Okay, compression ring or oil scraper ring. Actually, the diameter of the piston ring is slightly larger than the cylinder bore. Okay, the diameter of the piston ring is larger than the cylinder bore. Okay, the piston ring is to be fit into the grooves. Okay, on the piston barrel, and then to go into the cylinder bore. A part of the piston ring is cut. The various are cutting the end of the piston ring are shown in the figure. Okay, we have seen to how to calculate the radial thickness of the piston ring. Okay, denoted by the TR, radial distance of the piston ring with piston ring. See, B is equal to B, or we can say the TR is equal to D into root of 3 PW divided by sigma T. Again, PW is the allowable radial pressure on the cylinder wall. This is given in Newton per mm square. Okay, radial wall pressure in between the piston ring and the cylinder wall, the range is given 0.05 to 0.0042 Newton per mm square. Sigma T is the tangential stress, okay, or permissible tensile stress for the ring material. This cast iron material is given, range is given 85 to 110 Newton per mm square. Then axial thickness of the ring, this is axial thickness is given minimum is equal to d by 10z, d by 10z. A large of the two values you have to choose. Okay, z is again number of piston ring. Okay, see, before assembly you have to check that both value. Yes, gap between the pre-ring ends, it is given for the G is equal to 3.5B to 4B before assembly, and after assembly in the cylinder, this gap between the pre-ring ends, this G is equal to 0.02D to 0.04D. Here I have shown in the figure. Check that the gap between in that two pre-ring ends. Okay, the gap should be sufficient in between the ring. Okay, and working condition area of the highest temperature, the end should be the touch to each other. Okay, remember that. Then this value is given, G is equal to 3.5B and 4B. Okay, in today's lecture we'll stop here. Next lecture we'll see the remaining part of the piston, how to design of the piston skirt, then design of the piston pin. Okay, then again we'll see up to that, we'll complete that piston part. Okay, in today's lecture we have completed the piston part. Okay, piston ring is there, then piston ribs and cup is there, then heat dissipation and strength we have seen the both. Yeah, we'll get the which is the uh, greater value. This value you should choose for the design. Heat dissipation having the different formulae and strength having the different formulae, but you have to check which is the greater value. On the basis of that two value you should choose the value for the design. And what is the design requirement for the piston also we have seen. Okay, today we'll stop here. Then next lecture we'll going on the next part. This is the piston barrel. Okay, today we'll stop. Thank you.